So unfortunately, we will be using TS code or TypeScript for this, just because that's what my course is going to be in for algorithms part 2. TypeScript gives you the illusion of types without actually having types, and it makes people feel warm and fuzzy. So we're just going to do that, okay? It is what it is. So F you if you don't like it. Okay, you can suck my face. TS node, TypeScript. Is there anything else I need here?
I love you.
I don't think I need anything else here. Types node. We'll probably definitely need that. Classic environment, right? You got to set up 9,000 things just to get anything going. There we go. TSC init. VSTS config. And go dist or outdir. There we go. Bam. Hit him with one of those and
Welcome
go
to
dist.
Costco.
I think that's right. Get him with all those things just in case we need it. Hell yeah, girl. Thank you, Kelney. I appreciate that. And Deucey. You know, we all like a good Deucey. Active for a place to start learning about live video processing. I have no idea, Beef Nozzle. Probably I'm looking big. I'm looking swole. Not feeling swole today, though. Okay, anyways, let's give a little source. And let's go some dynamic. So just so you understand what is dynamic. Let me give you a quick example. Factorial, right? Easiest one, right? So you could technically solve factorial with recursion. You can literally just go factorial and you'd want to do tail recursive, right? There you go, right? So this is the recursive solution. Obviously, the factorial, dynamic would be the exact same thing, except for we go for let I equals 0. I has to be less than n plus I. Do one of those. And then what do we got to do? We got to go like this. Sum if n is, let's see, greater than or equal to 1, return 1. Yeah, that seems right. And you know what we could probably do? We could probably use like a little while loop, probably a little bit easier. What is it? Sum product. People are like, well, you gotta use product. If you don't use product, you're kind of an asshole. All right, while n is greater than or equal to 1, and do this. Okay, return product. That sounds about right, right? There you go. Pretty straightforward. Right? You're right. Thank you. So there you go. Pretty straightforward. You get the idea, right? You do something in which you have a lookup table. Now there's no these are effectively no dimensional problems, right? Pretty easy because you only need the sum. So Fibonacci, I think, is probably the most famous one, right? So if you do fib, like your standard Fibonacci, you'd go something like this. Return fib of n plus fib of n minus 1, right? I always forget. How does Fibonacci work? You take your current number and you do the rest, right? Hold on. N minus 1 and n minus 2. Dude, I can't even remember how this thing works. And if n equals, what, 1? Fibonacci sequence is 1, 1, 2, 3, 5, 8, right? Is that correct? I always forget. Here. If n is less than or equal to 1, return n, or just 1. Else return, yeah, okay, so I have the same answer. Okay, cool. Now, Fibonacci dynamic, of course, fib fast, right, is this. And so that means we're going to go like this. We're going to go let, I guess, A equals 1, let B equals 1, right? And then we have to go like this. For let I equals, what is it? 1, I has to be less than n. I think that's right. I have to do this off the top of my head. A equals, oh, we already had a temp. So they're saying this one. Yeah, that seems about right. Yeah, swap them down, move them up. Yep, I like it. Return B, right? Yeah, that makes sense because you're always in the highest position. I think that's right. Maybe? Yeah. So let's go like this. Fib fast. How about 20? And then we'll just go Fibonacci. So just so everyone sees the difference, go like this. NPX, TSC, source dynamic, right? Console.log, fib fast. Oopsies. There we go. So you can just see it probably starting right away in this one. Okay, apparently I didn't get the console log. Did we miss the console log? Are we missing it? Oh, I'm doing TSC. That's totally the wrong one. We got to go TS node. That's the one I wanted to do, right? Call stack exceeded. What happened if 1 equals 1? Wait, which one is this one? If 1 equals 1, if 1 is less than or equal to 1. All right. Well, let's try making this thing larger. Okay, there we go. We're starting to feel the difference now. We're starting to feel the difference now.
Welcome to Costco. I love you.
Ah! That would have been so sweet. Tell me that would not have been so sweet. It's only going, the stack's only going 40 deep. So why is this happening? Well, it's actually pretty easy why this is happening. I forgot I even had that there. That's pretty awesome. Hey, that's pretty neat. All right, so why is this happening? It's actually pretty simple what's happening here. You can imagine the following, right? Is that when you call, so if we call with 1,
That scared me.
Lith my babe. Okay. I'm whiteboarding right now, okay? We're whiteboarding, okay? We're whiteboarding. Fibonacci's trying to be solved recursively still. Nobody knows what the hell's happening. Lith my biff. Thank you very much for that. I appreciate it. You called me a lithium. Oh, lick me Thank you very much. I appreciate it, lithium. Let's go! I hope you guys are enjoying yourself. Let's go! I don't know what happened, okay? I don't know what happened. It's still going. I don't know what's going on, okay? Nobody knows what's going on. Okay, so with the thank you, Lithium. I do greatly. Damn it, Lithium, I appreciate it. Okay, so anyways, with 1, we do this. Now with 2, the darndest thing happens, right? We actually have to do 1, and we have to do 0, right? So we get 2, 1, 0, which this just turns 1, 1, which turns into 2, all right? Then at 3, though, we have to go like this. We have to do 3, which does 2 and 1, right? 2 and 1. And so this becomes 1. This becomes that, right? You can see the growth here, right? So at 4, what happens here? 4, well, you do 3 and you do 2. Well, here's the thing. Notice that 3 does this, 2 does that. Look at the repetitive nature of this. That means we recalculate 3 here, which recalculates 2, which we're calculating here, which 2 calculates what? Like, it goes really, really shitty, right? So recursive solutions, there we go, we're done. Recursive solutions can feel really simple to do, right? But they're not always that great. So now we're going to try to put our brains together, and I'm going to try to remember an old, what is it? The Academy of Machinery and Computing? I can't remember. Academic Machinery and Computing? Tell that to my algorithm teacher. Okay, well, your teacher, remember, your teacher lives in theoretical land. Okay, you go suck those theoretical eggs, understand how the theory works, and guess what? Nobody cares. Oh, who's the guy in the background? I don't know. Just the champion of Twitch. Okay? This man right here, he was the one that inspired the phrase, how do you kill that which has no life? Okay? Don't talk bad. Okay? Old school Blizzard employee. It's great times. Tom, no. All right, anyways. I heard there's one thing once, tail call optimization. Yeah, I mean, that works in some situations. This, it don't work, bro. So you know what I mean? That's Thor's dad. Yeah, it's Thor's dad. Anyways, that man is a lawnmower. Facts of life. Anyways, so not great, right? Memoize that bitch. That's also the wrong answer. The wrong answer is to solve it like this, right? The right answer is that to solve Fibonacci, you only need the two numbers you're working on, right? Because the next sequence is add these two together. That's your next sequence. Add these two together. That's your next sequence. So that would be a dynamic problem. A dynamic problem is where you can use effectively a counter of some sort to solve a problem that otherwise would be very, very difficult. And you see these kind of they're very interesting problems, and they're super exciting, right? So I want to solve a different problem, and now I was able to solve this when I was younger. I can't solve it today. I'm not going to lie to you guys. I'm too stupid now to solve it, but we're going to see if we can fix it. So here's the problem. The problem looks like this. Let's pretend we had the following items, and so we'll look this up maybe in a little bit. Let's just say this. These are our currencies, all right? Now, these currencies, let's just say that I give $500, right? How many different ways can I make change with $500 given these currencies? We probably need a 1 in there to always guarantee that it can be made. There we go. It's a fun problem, right? So this is also a dynamic programming problem. Kind of fun, huh? So I can't remember all of the requirements. By the way, did you just see that? I nailed to the pixel where I need to do that line. Tell me how awesome that is. Tell me how awesome that is. Tell me that was not great. All right. So I cannot remember the exact answer to how to solve this though, but it goes something like this. That what we're going to have to do is we're going to have to create a table. And that in this table, we're going to start off with the simple answers, right? The answers we already know. That's how dynamic programming problems work, is you start on problems you already know the answer to. So if our change was 0, there are 0 ways to make that, right? So if we only use, our ones, and this is how much change we need. At 1, well, there's only one way to make change, right? At $2, there's only one way to make change, right? At $3, there's only one way to make change, right? Is this making sense, right? No, there's only one way to make change. When you only have one type of currency, there's only one way to make change, which is with ones. Guess how much for 3? There's only one way you can make change. Guess how many for 4? There's only one way when you have ones you can make change, right? So now there's a 3, right? So I think I remember how to do this. So can't make change. We cannot make change. We can make change. Right? Right? So at this point, we can make change with our $3. Now, this is what I can't remember. How do we do this? What is the chance that the music is literally saying change right now? So I'm trying to remember how you do this correctly. I know it's the power of modulo, but I cannot remember the exact. Because in other words, you can definitely use 3 and you can use ones. So there's definitely two ways, right? So this should be a 2, but I'm trying to remember how would we calculate that it's a 2? Right? Let's just keep on writing it out. Let's see what happens. This is typically how I try to figure out these DP problems. right? Let's do a 2 again, right? At a 4, there's 2 ways you can make change. That makes sense, right? That makes sense. At a 5, at a 6, we now have hit something special, right? At 6. We now hit 3. But why? I have no gosh dang idea. All right. I'm trying to remember how to do this. Okay, so let's think about this. I don't want to look anything up. I'm just trying to derive the thing myself, okay? Because the thing I don't want to do is I don't...
Welcome to Costco. I love you.
Let's see, hold on. Let's see. Why are there 3 ways? Why are there 3 ways? Well, you have 3 plus 3. You have 3 plus 3 ones. And you have 6 by 1. So you have 3 by 2. Yeah, there you go. I am too stupid. There is always a 3-way, baby. That's the answer. Disgusting. All right. So my guess is what I'm doing incorrectly here is that you don't start at a 0. Let's get rid of that 0. I feel like the 0 is misleading us. Let's get rid of the 0. 0 does not exist. Can we all agree with that one? I feel like the 0 is misleading us. All right, clear our mind, people. Listen to the music. And then the next thing that I think is actually misleading us is these zeros. I think they should be 1s. All right, I think they should be 1s. So let's think about this. Let's think about it. Let's think about it for a second, okay? So let's give the change of 6. How would we derive this answer? Gosh, I know there's a table hop strategy. There's a hop in here, and I do not see it, and I don't know why I don't see it. What the hell is it again? Dude, I just remembered so well that it involved hopping down the table. And it was so simple. Man, I'm such a dummy. All right, I am such a dummy. Cook Daddy, I know, just let's try to see it for a second, right? Just add another row and analyze the pattern. We can add another row. Hey, Rambo, thanks for those 2 bones, baby.
Here's a challenge. Say the opposite of every word. Always, coming, from, take, me, down.
That is a great Rickroll, by the way. I just could never possibly say it that fast. All right, anyways, there's only one way to make change. There's only one way to make change. Actually, you know what? I feel like maybe these are supposed to be 0s. Okay, hold on. Maybe I'm doing this wrong. Hold on. Maybe I'm doing this wrong. Hold the phone. You know what I mean? Maybe we're doing this wrong. Maybe we're doing this wrong. Maybe this is supposed to be 0s. Okay, just hold on. Just hold. Let the man cook. No, that can't be right. Hold in firmly. No, it can't be right. That can't be right. Can it be right? Can it be right? Damn it. I'm going to have to look this up, aren't I? I'm going to have to go through this coin sorting problem. This was just such a magic problem. All right, so if we're handed a 6, how do we arrive to the solution of 3, right? All right. How do we arrive to the solution of 3? Is the problem, is this problem considered hard? I think it's hard. Wouldn't 6 be 4? Why would 6 be 4? Explain yourself. This is change making. You already missed that there's 3 ways to get 3. There's not 3 ways to get 3. There's 2 ways to get 3. There's not 4 ways to get 3. Order does not matter in change world. Guys, change does not matter if someone hands you a 3 and then a 1 or a 1 then a 3, right? There's not like this multi-paradigm. We don't live in some stupid-ass world where that actually makes a difference, okay? It doesn't make a difference. All right, so yes, at 3, there should be 2 different ways you can make change. Okay? At 6, there should be 3 different ways. Now, I'm trying to remember. Damn it. Okay, let's start looking at. Oh, I read the 3 wrong. At 3, there is 1. No, at 3, there's 2. Shut up! Goodness gracious! At 3, there is 2! Okay, chat, I can't talk to you. You're too. You're not in. Okay, you're not. Tighten it up. Okay, tighten it up. Okay. Tighten it up, and I mean it. All right. Let's call this coin change problem. Okay, I'm too stupid. I can't remember it. It just got here. Sorry. Want to talk to me, Beastco? You are very, very amazing. All right. Given it. Thanks for showing my. Got any more pop-ups? Got any more pop-ups? All right. Anyways. Given an integer array of coins, a size n representing the different types of currency, and an integer sum, the task is to find the number of ways to make the sum by using different combination of coins. Note, assume that you have an infinite supply of each coins. Example. Beautiful, right? This is pretty beautiful. Okay, hold on. Someone's trying to, because I'd like to. Let's see.
I love you.
Unfortunately, here. All right. Whatever you just gave me. I'm not looking at that again, okay? Okay, here we go. Coin change. Solve the, let's see. Okay, solve the coin change is to traverse the array by applying the recursive solution and keep finding the possible ways to find the currency. You know, okay. Interesting. It should be noted that the above function computes the same subproblems again and again. Yep, that's true. That's true. There are 5 solutions. Okay, good. So the recursive way is to, let's see, traverse an array by applying the recursive solution and keep finding the possible ways to find the, yep. Okay. It should be noted that the above function computes the same subproblem again and again. See the following recursive tree. So this is always, by the way, this is the good sign. This right here is the sign that you're in dynamic programming possible land, right? Elementary solution, oh, my dear Watson. Let's see, function this right here is called 2 times. If we draw the complete thing, yep. All right, so maybe it would be, maybe we should try to solve this recursively first. Because I don't want to give it away. I want my brain to rediscover it, right? I want to feel the thrill of rediscovering it. Do you want to do that? So let's first delete that very lovely piece of ornamental ASCII art. And let's go like this. Function, change my coins, daddy. All right. And this obviously is going to take in denominations or coins. And this is going to be a number array. And then we're going to have, I don't know, total change. The amount of we need to make change with, right? And we need to return a number. All right, so let's think about this. So the iterative solution wouldn't be too hard in the sense that is the iterative solution hard? I'm not even sure how to do the. I've done the iterative solution once. It was awful. The iterative solution is just awful. Anyways, all right. So let's think about this. If you want to make change, assuming these coins are sorted, right? I think I can make the assumption that these coins can be sorted, right? And so one way is that there should always be a 1, right? There's inherently, you always have to have a 1. You have to have a 1 because if you don't have a 1, you may not always be able to make change. As simple as that. There always has to be a 1. And I'm going to make those two assumptions, that the coins are sorted. There's always a 1. Because none of it else makes any sort of sense. Okay, so now that we got that out of the way, I feel like this is what I feel like has to happen. I feel like I'm seeing it. Okay, are you guys ready? I feel like I'm seeing it. I see the tree. I see. It's not a tree. It's a forest of trees that are summed. Okay, I see it. Okay, I see it. Okay. So let's pretend we had 1, 3, and 5, right? Pretty straightforward. Draw the motherfucking tree right now. All right, and we got to and let's just say we're going to do the number 25. This is way too large, but let's just pretend we're going to do it. Okay, so while we're doing this, what we need to do is we need to create a little tree spot for each one of these, right?
Welcome to Costco. I love you.
And this is how I'm thinking about it. If you're a 1, you simply return a 1. Okay, so if coin, okay, hold on. So something like this. If let's see, I feel like I need like an index. Let's just throw an index in here. Throw an effing index in here. I don't know yet. Okay, I don't know yet. If coins index equals 1, we return 1. There's only one way to make change when you have a 1. It's just all 1s. That's all there is to it. Okay. Easy peasy, pumpkin seedsy, okay? See, Mom, anyone can program. Yeah, thank you. Okay. Brian's, oh, no, I think I solved this. Jang, thank you very much. Ads popped up as I was watching, so I had to resub. Oh, thank you, Jang. I appreciate that. Dawes Days, thank you for the tier 1. Let's go. And Ampere's Law, thank you for that Twitch Prime. Is taking an ad break. Still sees Prime in the corner. Liar. I'm taking an ad break, Mom. All right, so does that seem right? This feels right, okay? All right, now here's the deal. While, all right, am I right on this one? Hold on. Okay, so in my head, what we need to do, this is kind of like my thoughts, is that let's just work through the 5 situation. The 5 situation, what I can do
Welcome to Costco.
is I can take that 25. Hey, I love you too, Daddy. I can take 25 and 5, which is 20, by the way. Quick math right there. Okay? I can take 20, and this is one way to make change with the 5. Now I take this 20, and I now need to make change for 1 and 3. Okay? Do you see what I'm doing here? Do you see that? Okay? Is this starting to make sense? I feel like this is good. There's also going to be a 25 minus 10, right? That's another way to make change, right? Which then we're going to need to also solve everything below it with the different ways to be able to make change with 1 and 3. Oh yeah, I feel like I'm seeing this. Oh yeah. Oh yeah, I feel like I'm seeing it. Did I just take acid? Nobody actually knows. Okay. So now you can do 25 minus 15. This is another way, right? Which is going to be 10, 1 and 3. Can we all agree with this? This is all looking good. This is all looking good, right? Aware, yeah. We can also do 25 minus 20, right? Which is going to be 5, 1 and 3. Does this make sense? All right, does this make sense? Like, I can see this, right? This is technically correct, right? There's like 5 states you can be in, and then the last one, of course, is 25 minus 5, right? We can also make it with all 5s, right? So, boom. So, this is the different ways in which we can use 5s to make change, right? Okay. This is pretty good. So, this is probably where that table comes in, where you do the numbers, right? Okay, I think I'm seeing it. I think I might be seeing the table all of a sudden. Okay, so there we go. So we got this one. So this is like 5, right? Yeah. Okay, but then we got to solve this thing right here. So now, let's just go over here and let's do 20 for 3. I should have picked a smaller number. Well, rub my nipples in cream. This is ridiculous. Okay, let's just pretend we have 1,
Welcome to Costco.
3, and 5, and we're solving the number 10. And okay, so that means we can use 0 5s, which gives us 10, which means we can make change with 1 and 3, correct? So here's version 1. Version 2 means we can make change with 5, 1 and 3, right? We use 1 5. Version 3 means we can do it with 0, right? We use all of our 5s, and we make change with this. Okay, does this make sense? Okay, does this make sense? I feel like this makes sense. So there's 3 possible ways to make change for 10 with just 5s. Now we have to sub-break down this problem. Now, on a 3, we can make change for a 10.
Welcome to Costco. I love you.
With a 1, right, we used the 0 3s. We can do it for 7, and we can use 1 to make the rest of the change. We can do it for 4, 1, right? Those are the possible states from 10. Does this make sense? Those are those possible states right there. We can make 4 more different ways to make change right here effectively, I think. We can use... Oh, let's just make sure we got this one right. Let's just make sure we got this right. Hold on. Right? And all these can be solved with 1s. Okay. Then obviously 10 1 is just 1. That's a bonus 1, right? You can only solve this one way left, right? On this one, we can only solve this with one way left. On this one, we can only solve this with one way left. On this one, we can only solve this with one way left. So in my head, let's just validate that this is true. The amount of ways to make change at 10 is 8. Am I correct? With 1 and 3. I'm not sure. 1, 3. Let's find out. All right. So let's see. 1, 2, 3, 4, 5, like 6, 7, 8, 9, 10. All right. So for 1, there's only one way to make change, right? All the way through. All the way through. There's only one way this entire time. At 3, you cannot make change here. You cannot make change here. You can make change here. You can only make it, well, I mean, that's the problem, is you can actually technically make change 2 ways here. Because you have this. At 3, you have this plus this, right? So the real question is, should this be a 1 or should this be a 2? I'm thinking it should be a 1. Let's just try it with a 1. So with 3s, there's only one way to make change. Until you get to here, then there's 2 ways to make change. Right? And then at this one, there's 3 ways to make change. So if we were right here...
Welcome to Costco.
How can we traverse this table to make any sort of sense? So I said there is going to be how many different ways? 1, 2, 3, 4, 5, 6, 7, 8. Is that fair? Add down. So there's 8. So what happens if we do 3? See, I'm just sorry. I'm trying to do math, quick math. Okay, so here's what I think. Here's what I think. 3. This can't be right. I feel like I'm doing something wrong here. 3 plus 1, because it's all the rest of the stuff below it. Subtract by 3, move us this way. 2 plus 1, I don't even know if this is going to work out. So where are we at? We're at 4, 7. Subtract 3 more. 1 plus 1. That would put us at 9. Subtract 1 more, that's 10. Okay, so I think I've done something wrong here. Whoopsies. I think I'm too stupid. I think I'm off. I'm off smoking something here. Okay, so I don't think that was it. I don't think I quite did it right. All right, what's chat saying? Let's see. 4 at 10. 3 times 3 plus 1. 3 times 2 plus 1, 1, 1. 3 times 1 plus 1, 1, 1. So there are only 4 at 10. Oh, really? You're right. I double counted. Okay, so something about this. Now, I wonder if there's a multiplication or something going on here. I think I'm missing a multiplication. So this times this is 4. Wait, this would be addition. This is 4. So, I mean, I see a 4 right here. What happened if every time you use one of these keys, what if, oh my goodness, wait a second. What happened if the answer was right in front of me this whole time? What if the answer was right there this whole effing time? What happened if it's this? And this. I feel like that could be it. Okay, let's find out. What happened if the answer is right there this whole time? I need to get a 7 in there somehow, right? I need to get a 7 in there because a 7 really screws everything up, right? It screws up my quick math. I can't even do it. I don't get that. Okay, so anyways. So let's go like this. Let sum equals 0, and let's do a do-while loop. You know why? Because we're badasses around here. We can't do a do-while loop. We never do a do-while loop. You don't ever do a do-while loop because that's disgusting. While change, let's see, let coin equals coins index. While change is greater than 0, right? While change is greater than 0. Yeah. Wait, no, while change is greater than coin, right? Greater than or equal to coin, right? Right? I don't know if I even got this. I don't even know if I got this thing even close to doing it correct. But let's just find out, okay? Only use do whiles with atomics. That's right. Only do while. I woke up from back. Send message to you from YouTube's chat. He keeps saying use the AMB operator. Okay, I don't care about whatever some turd is saying. Okay, I'm trying to remember from my own head. Okay, I'm trying to remember from my own head. There's something here that I'm missing, and it's so obvious. It's right here. I can feel it. It's like tickling the back of my brain. You know what I mean? Depth first search. Get the out of here with that kind of nonsense. Okay? You can't become trotting in here, tossing out a DFS on us. Okay? We're not talking about DFS's dog. Okay? Whatever you're just saying right now makes no sense. No. Stop trying to give me only the answer. Okay? I'm not. Stop it. We're trying to think about this. So if I were to solve this recursively, what you're saying is, at this point, with what is remaining, technically, I'd have to do a, this is kind of what I'm thinking right here. This is exactly what I was thinking, is that I do something like change my coins daddy, right? And I would repass in the coins. Remaining would remove off the coin because remaining wouldn't remove off the coin. I need to get the sum from there. Then I need the index does not, no. The index, let's -1, right? Actually, you know what? We can move one of these out here. Because technically, change my coins daddy can take in the coins and hit him with the remaining and IDX -1, right? We can always just not use it, right? We don't have to use it. And then this is, I think, where the do while is close, right? The do while's really close. Where I really wish I had a do while right now. I just want it so bad. I just want to do while so bad. It can't be the sum. This doesn't feel right. It doesn't feel right.
Welcome to Costco. I love you.
This doesn't feel right, right? This doesn't feel right. Something about this doesn't feel right. All right. While remaining is greater than coin, we're going to do a little
Welcome to
change
Costco.
my daddy, coins.
I love you.
Remaining minus coin. Remaining minus equals coin. And then we need to calculate all of them below us, right? That seems right. Like, I think this is right. If remaining is greater than 0, well, then we need to do, I don't even know if this is true, right? So I don't know if this actually is correct at all. I don't know if that's correct. I have no idea. I have no idea if this is correct. Okay, I kind of made it up. And I kind of feel like, have you ever been... Never mind, I was about to say something real stupid. Okay, sometimes when you've been... I don't know why that's bothering me. I just want to use remaining here. It feels better. Overflow, bomb, and pending. Potentially. We're going to go like this. If coins IDX... If IDX equals... is less than 0. I'm not exactly sure how we got here, so we're just going to return 0. That seems like a stupid way. Okay, but, it could happen based on my current thing, right? It shouldn't actually happen, right? This should technically never happen. Technically. Technically, it should never happen. IDX. So this is where my Java skills come into play. Are you ready for some sweet Java skills? Change. You'd pass in the coins, the number, and the amount you want. Change, right? Which is some number. And this is where I'd return my private method called change my coins, right? Look at that. Look at this. Look at my Java, okay? We call that like a header to recursion. That's not true. I would always assume I am assuming that the change is coming in is definitely coming in ordered. Okay. So let's go like this. Change. Let's just try our 1 and 3 for 10. Okay. Let's at least prove that I'm probably too stupid for this. And then let's go like this. Console.log. Honestly, I'm probably too stupid for this. Okay. I'm just telling you. Okay. 5. I feel like that was wrong. And plus, I never really did something here. I feel like I need to add 1 somewhere. I'm missing a way to add 1, right? Right? Shouldn't there be like a +1 somewhere? Like, I feel like I did that wrong. Maybe I'm double counting now. Okay, so I feel like I've double counted now. We've reestablished this 8. Remember that? But there's not. There's not that many ways. Okay. Gotta add 1. Okay. I really gotta pee. All right, so obviously I don't know what I'm doing. I don't quite see how to solve this problem at all. I feel like I'm so close. Right? The problem looks like this. So like in its purest form, wow, Pascal people love that word. In the simplest form of this, you have a change, we're gonna call it C, and you have coins, which we're gonna call CS, right? And it seems like we have to loop over our change with taking out our current index, right? So we actually have a certain coin, right? Whatever coin we're on right now, I, right? We have to take out our current coin, and then we have to count down from the change and make change from everything below. And there's like a +1 in here, right? That's what I see. And then all the different ways.
Welcome to Costco.
You know,
I love you.
this is what it feels like. It feels like, all right, every time I reduce our change, every time I take out a coin of change, right? Our change minus our current, our current coin, we're going to do 1 plus, right? 1 plus the amount of different ways we can with this remaining value. That's in my head how it is. All right. Right, so yeah, there you go. So you have 1, 2, 5. There we go. See, so this is actually how I was looking at it in my head, which is then it would recreate this thing right here, which is 1, 2, 5, which is then 1, 2, 3, which is then 1, 2, 1. Yep. Okay, so that's how it was working in my head. This is what I've attempted to create. So don't count duplicates. I mean, in some sense, you have to count duplicates, right? You just can't. To make a change for 5 is the same as making change for 4, which is the same as making change for 3. See, this branch right here should be only counted as 1. All right, the following steps. We have 2 choices for a coin of a particular denomination. Either I to include or I or to exclude. Okay. Count of remaining is equal to 0. Is this thing Pascal's triangle? Maybe. I don't know. If we are at coins n-1, we can take as many instances of that coin, unbounded inclusion. Okay. Coins, count coins n, sum minus coins. Wait, what? Okay, they're solving it very similar to how I did it. Okay. So coins, n is, my assumption is where within the coin, it's their index. I called it index. They called it n. And so sum is the total amount. Okay. So we can literally do this. Okay, this makes sense. I think, yeah. Yeah, as long as it's within. Okay. Okay. Tom would have already solved it using Bitcoins. I know. I'm so stupid. Finally, we have to find the total number of ways. So we'll have to have 2. Okay, so I got to go pee. I got to be right back. I got to pee. I got to pee. Ugh. Respectfully, this idiot should have just used J Diesel. I'm not going to lie to you. You're probably correct. You're probably correct. All right. Yeah, I've never liked Geek for Geeks either. It just is the first one. They've mastered search. They've somehow mastered search algorithms, right? Netflix engineer, by the way. Yeah. This shit's hard, okay? Okay. So, you know what? Check this out. This is what we're going to do, okay? This is what we're going to do. I don't know why it was so obvious. First off, I'm going to change it like this. I like this. And I think the first thing I did wrong is that I didn't have a do while loop, okay? I did not have a do while loop. That was my first problem, okay? While remaining is greater than 0. Okay? It seems obvious this is what I wanted to do right here. Right? It seems obvious this is the way I wanted to do it. Reason why is that I can calculate everything below. Right? Now we're cooking, right? Calculate everything below me, right? Because we don't use the coin. We calculate everything else, right? Because if we're at, say, the 1 and the 3, and we're solving for 5, well, the first thing we can do is, okay, we can make a change of 5 ones. Yes. I feel like that makes sense. And so if I pull this thing in, and this thing equals 1, we should have it. Perfect, right? Okay, good. We're looking good. We're feeling good. We're licking nipples and everything, right? Then we're going to minus the coin. And when we minus the coin, I feel like we need the sum. See, I feel like this is where we want to add 1 to the sum, but this is where everything gets all jacked up, right? Do we not want to add 1 to the sum here? I think that's right. Yeah. We don't want to add 1 to the sum because we're recounting it. We don't want to add 1 to the sum. You don't want to add 1 to the sum. All right, so now if we add in a 5, this should only increase. So we do have one problem. If we land directly on 0. Right? If we land directly on 0, we want to do that. So this should yield the answer of... Okay, I feel like I now see it. What is the answer of this one? Well, we can get 2 more ways to make change, right? Am I correct on that? 3 ways. Oh yeah, 3 ways. You don't have to use it, that's 4. Then you have then you just have to make change with the 5, which is all 1s and a 3. So that's 2, right? Right? Did I get that right? Is that right? Can someone solve... Okay, hold on. I just want to make sure I got this. So 10. We have 10 by 1. We have a 5 by 1 plus a 3 by 1 plus 1 by 2. Yep. Yeah, there we go. Plus a 1 by 2. We have a 5 by 1 plus 5 ones. Correct. We have a 3 by 3 with that one. Correct. We have a 2 by 3 plus 4 ones. Yep. And then we have a 3 by 1 with 4 sevens. Correct. And then we have a 1 by 10. This feels correct. And that is 7. All right. I now believe I have solved the solution. You're right. Well, that's because I did 10 by 1. This should be, sorry. This should be 5 by 2. Right. There we go. 5 by 2.
Welcome to Costco. I love
7.
you.
We've achieved it. We've achieved it. We've achieved it, right? We've achieved. What's making those suggestions? AI. AI. Yes, it is. It's 5 by 2. Everything else is correct. Yeah. This is correct. This is it. Okay. Okay, so I feel like we've done it. Can we all agree my recursive solution is probably correct? Here, let's try it out on their stupid choices, right? Real voice leak? Yeah. All right. What's the answer? I don't want to look at their... I mean, I guess we can look at their thing now. All right, if sum equals 0, then we return 1. Okay, if sum's less than 0, we return 0. Interesting. Okay, they solved it there. Good move. I liked what they did. I actually liked how they did that. Oh, this is interesting how they did it. Oh, they went full. I went partial, iter, partial. Okay, yeah. Okay, this is cooler. All right, if n is less than 0, 0. If there is no more coins to sum, yep, 0, 0, 1. Okay, makes perfect sense. We do coins. What the fudge is 0? Okay, n is position, right? Yes. Oh, that makes sense. We sum everything at our position, just one below. This makes sense. And we sum everything at our position while we keep the same n. Oh. Oh, that makes so much more sense. Okay, do you see how their solution works? Do you see what happens there? Their recursive solution's clever. Makes a lot of sense. Damn. Okay, so see how I did a do while? What did I just do here at this position? The very first time through, this effectively is only moving the index down. Look at what they do here. They only move the index down the first time through. The second time through, then after that, I remove a coin and then I redo it, which is what they do right here. They remove a coin and then re-go through this solution again. Do you see that? I'm doing the same thing. I'm just partially doing it in a while loop. Does that make sense? So I'm doing this and this in the while loop, whereas they're not doing it. Is it any better? Obviously, it doesn't really matter. They both are bad solutions, right? But this is correct. We've done the exact same thing. True, but yours would probably going to be slow AF. I'm pretty sure neither of them matter. They're going to be both slow AF. Okay, I'm not sure how much tail recall like optimization you get when you have two positions of recursion, okay? I'm sorry, I hate to break the news to you, but that's just not how these things work, okay? Oh, it's fast now. One of them is less shitty than the other one. Interrupting deep thought for this important message. Hey, Durkartafafel calling on Knack. Thank you very much for that tier 1. A Suicide Bunny 666. What a name. Thank you for that Twitch Prime. Sorry I didn't say anything. Stellar! Thank you for that Twitch Prime. Appreciate that. And the ironic anime girl. Sorry. There is no capital letters in that. Do you see how I'm like, I'm looking over here like, the iron I can, I'm e-girl. The iron I can, I'm e-girl. The iron I can! I thought you were flexing on me. I didn't realize. E-girl. Yeah, I'm calling you E-girl. Can I call you E-girl? Is that okay? Are you still around? I feel bad I didn't say anything. But I feel like this is totally legal to call you E-girl. Okay. E-girl might have left an extreme upsetness at me not saying thank you for that, and I feel genuinely bad. And Killrain, thank you very much for that Twitch Prime. Sorry, and Gills, thank you for that resubscribe. I can't believe I missed this. Prime Simpin, yeah. Ligma Spheres, absolutely. Instead of making a tree, you could use a sum from the bottom
Welcome
up.
to Costco.
That's what we're going to do.
I love you.
I think that's what we're going to do. Cold Sun 99, thank you very much. And Nullberry, dude, I missed like all of these. Where was I? Thank you very much, Nullberry. A tomato. Thank you very much. No, we're not benchmarking anything. Okay.
Welcome to Costco.
I love you. Hey, Snaky Bat. Thank you very much for that. I appreciate that. Okay, so we have done everything. We're looking good. So now how? Okay, so let's try to spot some things from this little biz right here, which is okay. So when there's a correct, okay, so this actually, I like what they've done here. Do you see this? This is actually pretty clever. In a sense, mine's also clever. Whenever you hit the one change case, you've made it, right? That's all there is to it. Whenever you hit that one change case, you've already made it. There's no need to keep on going. You don't need to call all the way down a bajillion times to make it, right? I think that makes sense. Right? Yeah. Okay, the coding problem isn't hard. Okay, so we got something here. So how do we do the ones? How do we start adding these ones together?
Welcome to Costco. I love you.
Hey, tech savvy Travie. All right, so how do I convert this? Coffee Keeper. I honestly have no idea how to convert this, and I'm scared to check Lithium's message. Time complexity. 2 sum. That doesn't sound fun, huh? I don't want that. People linking me Theo's tweets. I'm not a furry, okay? Okay, clearly. Not a furry. All right, so we can kind of see the hopping through this table. Melky and shambles now. Okay, so we can actually see the hopping in the table. Can we all agree? Can we all agree we can see something about hopping in this table? Because what you're seeing right here is ooh, didn't nail that one. Didn't nail that. You're starting somewhere up high in this table, right? Right? Somewhere in this dynamic programming table, right? It's somewhere up high, right? And in this table, you kind of go 2 different directions. Can we say that that's true? You go 2 different directions to figure out how much you have left. That's effectively what's happening in this dynamic programming problem. Is that here you jump over by whatever this coin size is, right? So this CI, you're going to jump over by CI, right? And then whatever this position is, X0, you need to go down, and then you do it again. You know, this would be, I started with 0, that's probably bad, X1, and then you go down. And then you do it again, right? And we go down. Does this all make sense? Is this starting to feel good? Like, I kind of feel like we see the solution, right? And here's the deal. Hey. Gosh, this song is so good. Let's make another observation. Mother. Okay, are you ready for this? Are you ready? Are you ready to make another observation? Oh gosh, this is feeling good. I'm actually starting to sweat a little bit. I -1. Okay, check this out. When we go here and we hit the Y's, okay, we do the exact same thing. We're going to jump over by another amount. C I -1, right? Wow, I've chosen a terrible program for this, right? And we're going to do it again, right? And then we're going to do the exact same thing this direction. But what can we say from Y's position? Well, Y is going to do this again, right? Y is going to do it again. And then we're going to do it again. And then when we've reached the bottom row, when we've reached the winner's row, this is a 1. This is a 1. Okay? Okay, so you go straight down. Slap! That's a 1. Then you hop on over. Slap! That's a 1. And then you hop on over. That's a 1. Okay? We're starting to see something. But we're missing something from the table. We are missing something from the table still. Right? We're still missing something from the table, right? What is the thing we're missing from the table? It's almost like we got to start building up change a different way. Right? So what if we invert this whole thing? Can I get like that math thing where there's like, you know what I mean? Because I feel like this is how recursion works, right? The recursion is you start up here, right? This is how the recursive solution works. You start up there, and you're, what happens if we start from down here? And our goal is to get up here. Bottom up, boys. You know what? Tired of being a top? I'm ready to be a bottom. It's my bottom arc starting today. Okay? We're starting with 1. All right? But I'm not going to lie to you. Not going to lie to you. I can't quite say I understand this. Yet. All right, so let's go back to our 10. Let's okay. Anime voice reveal. There we went. All right, so let's do this. Oh, I almost nailed it. Let's go over 10. 1, 2, 3. Should be using something else at this point. 4. Should be using something else at this point, but why does it feel right? 5. Wait, hold on. I forgot where I'm at. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay? We're at 10. Okay? We got a little 10 below me. Below me. Right? 9, 8, 7, 6, 5, 4, 3, 2, 1. Okay, there you go. And let's just say all we have is a 1 and a 3. Well, again, as we've previously established, this is all ones.
I love you.
Ad infinitum. All right? Now, what happens if we start doing modulo this way? Okay? We'd have 1, right? Because this is 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay? I swear I know for a fact I'm close. I know that I'm close. Well, what about 5? So this is where we have to achieve the 7, okay? We have to achieve the 7. So these are all zeros. There we go. Until here, which now we're all ones until here. All right, so what I see is 1 plus the sum this direction, but that can't be right. This can't be right. This can't be right. This can't be right. This cannot be right. Okay, let's add in a 7, because I feel like we could do a 7 here, right? We're going to have to hand calculate out our 7. Actually, we won't have to hand calculate out our 7. We'll just go in here and go, let's throw in a 7. All right. And we need a 9er. Thank you. Give me strength towards that. All right. So here we have a 1 right here. All right. Which is only, it's still a 1. Right? We're still a 1. Hold on, hold on, hold on. Hold on. 5. See, that's 2, 5, 6. Can't be right. See, I'd put that as 10. So we can't do it that way. Damn it. I'm missing one thing. I'm missing one thing. What is the thing we're missing? What is the... I don't want to miss things. All right. All right, the coin change is a problem is a classic dynamic programming problem that involves finding the number of ways to make change from a given amount of money using a set of coins. Here's the step-by-step solution to the coin change problems. What am I missing? I'm so effing close. I know I'm close. I know I'm close. I'm upset. Here, let's see what chat. Let's see. Have you worked down from 10, adding 5, and now you have a... Let's see, hold on. You have to work down from 10. By adding 5, you now have a handle. Let's see, you now have to handle an extra case where you can use 3. Okay. I know that. You're kind of missing what the meaning of each cell is. Yeah, see, that's what I'm feeling. That's how I'm feeling too. I feel like I've missed the meaning of each cell. I'm totally on your team. I'm totally on your team because I feel like it should count upwards, right? I almost feel like ones need to go this way as well, right? I feel like ones need to go that way, ones need to go this way. Let's change this meaning, boys. We're going to change some meanings. Are you guys ready for some meaning changing? All right, let's try this again, because I feel like I'm missing something that's just right in front of me. All right. So here's where we hit the 2, right? There are 2 ways to make change at this point. Officially, there's 3 ways to make change at a 6. There's 4 ways to make change here, and there's 4 to make here. So, I mean, there's technically 4 right there. Right? There's 4 right there. Okay. If we were to add in this one, well, it inherits whatever's below it, right? Technically, it should be able to do this one. So then this would become 4. It's like I'm missing something. Something seems wrong here. I'm so missing something that it's like it's right in front of me. It's like I can taste it. Right? Oh, then this thing becomes 5. Right here. And then this thing becomes 6. That can't be right. See, I feel like I've missed something. There's 1 way. There's 2 ways. Then at 5, there's 3 ways, right? Because there's 5. Yeah. Am I missing something? All right, hold on. Make each cell be only the column modulo in each row's coin. See, I started there. I did start there, Ligma Spheres. And I felt like I was wrong. So I'm going to read, right? We're going to read here. All right. I'm just going to have to read. All right. Here we go. Let's see. All right, first off, define the problem. Given a target amount and a set amount of coin denominations, find the total number of unique ways to make change for the target amount of using the coins. Identify the subproblems. We can break the problem down into subproblems by considering the subproblem of making change for smaller amounts first. For each coin denomination, we can ask how many ways are there to make change for the remaining amount after subtracting the coin value. Correct. This is correct. Define the base case. If the target amount is 0, there's exactly 1 way to make change. Correct. No coins. If the target amount is negative, there are no ways. Okay, yeah, but we're not even worried about that. Define the recursive formula. Let dp sub I be the number of ways to make change for the amount I. Then we can calculate dpi for all I using the following formula. apparently we're going to be using SCSS. Okay, I knew people are using CSS for a back-end language, but I really don't understand it for dynamic programming, okay? Damn it, it's 9 o'clock. I told my wife I'd be back by 9 o'clock, and I want to be back by 9 o'clock. It's 9 o'clock. Dang it. It's 2 past.